inverse function style.
Well, that's right. Our topic tonight is inverses. So we've talked about linear inverses in the past, and today we're going to get a little more in depth with them. So let's recall what a function is. We said a function is something that passes the vertical line test. Basically, every input can only have one output. So what did it mean to pass the vertical line test? Well, let's take a parabola, y equals x squared. And if I draw that vertical line, I can only touch the function once in order to pass the vertical line test. So if I were to basically pick this line up and move it across here, it's only ever going to touch once. So I would say this is a function. However, a circle is a great example, or even better, a sideways parabola here. Okay, so like x equals y squared. Notice if I draw a vertical line here, I intersect twice. So this is not a function. All right, so moving on to inverse function notation. The notation we've used in the past looks like this. Well, let me recall, f of x was just fancy for y, and then my inverse notation looked like f, and it had a -1 up there, but we don't actually say it as -1. This is red, so let's put quotes around it, f inverse of x. Okay, we're taking the inverse of x. So let's get these general rules down. So in general, to find an inverse, the first thing we want to do is interchange the x and the y. Next, we'll solve the equation for y. And if already given a graph, simply switch the x and y coordinates to regraph it. So these are our three main ideas. Here are a few little extra tidbits about inverses. So let's make sure we get these down and understand these. If a function passes the horizontal line test, it has an inverse. Notice now we said horizontal, not vertical. And two, graphically, a function and its inverse are reflections over the line y equals x. So let's quickly graph these three functions, and we'll determine if they have inverses just by looking at the graph. So first of all, this is a function because it passes the vertical line test. Notice my red slash through it. This is a function, it passes the vertical line test. This is a function, it passes the vertical line test. So to see if it has an inverse, I'm going to test the horizontal line test. So basically, I'm just going to draw a horizontal line. Notice that horizontal line hit twice. So this does not have an inverse. Okay, over the whole domain. Now, if I restrict the domain, then it does, but not over the whole domain. Take a look at this guy. It'll pass the vertical line test because it's only hitting in one spot. So this will have an inverse. And so will this term. It will have an inverse. It's only going to hit in one spot. Now, the other tidbit we said was it should be a reflection over the line y equals x. So I'm going to go ahead and graph the reflections of the ones that have inverses. So its reflection would look like this. Let me draw on y equals x. Y equals x, remember, is 1, 1, 2, 2, 3, 3. And if I'm going to draw on my y equals x first to help myself reflect this over because it definitely has an inverse, it would look something like that. So two tidbits. If the function passes the horizontal, we know it's going to have an inverse, and then the inverse should be a reflection graphically over the line y equals x. So we're going to start with a nice feel-good question, one we've done before. Find the inverse of the function, graph to verify. So the first thing I'm going to do is, I'm first going to put it in terms of y. Remember, f of x really is y, so it's y equals 1 minus 4x. Okay, if you look back at your steps, we said interchange the x and y. So now it's x equals 1 minus 4y. And we said just solve for y. So what would you do first to get y by itself? Hopefully subtract the 1 over. So I'm going to say x minus 1 equals negative 4y. And then, of course, just divide both sides by negative 4. So my inverse, f inverse of x, is equal to x minus 1 over negative 4. Now, you'll notice the direction said we're going to graph both to verify. And let's go ahead and grab our calculator to graph both. So I imported my graph. I'm using the Desmos feature that we've talked about before. And you can see my first function is in red, and then its inverse is graphed here in blue. And again, because they are inverses, they should be reflections over that line y equals x. And let's go ahead and plot that. Now, unfortunately, I'm going to try to draw it as nice as I can, but I'm sure I'll be off a tad here. Remember, that's just 1, 1, 2, 2, 3, 3, etc. There's my line y equals x. And by reflections, what I'm saying is if I were to fold on this line, these two lines should land exactly on top of each other. Okay, so we've graphed our inverses, we see that they're reflections, and we should be good to go. So again, that was a friendly review problem. We're going to get into some pretty nasty ones in the next upcoming slides here. So example 2, f of x equals x cubed minus 3. So the first thing I wanted to do is grab my calculator and get a quick sketch of it. So you'll notice right away as we sketch it, and you can sketch it on your paper, this is a function. It passes the vertical line test. And to test to see if it has an inverse, before I do all the work, I know it passes the horizontal line test, so I know this function has an inverse. All right, so now we can go ahead and find it. So remember, f of x is really my y, so y equals x cubed minus 3. So step 1, switch the x and y. X equals y cubed minus 3. And now my goal is to solve for y. So again, just PEMDAS. What are you going to get by itself first? Y, of course. Add 3 to both sides. X plus 3 equals y cubed. Now, how do you get rid of a y cubed? Well, the cube, so to speak, not the y. You just simply take the cubed root of both sides. Cubed root that side, and I'm going to cube root this side. So I'm going to say y equals the cubed root of x plus 3. Now again, this should, since it's an inverse, be a reflection over that line y equals x. And let's use our calculator to verify and make a quick sketch with. And again, hopefully you can see that reflection. I'll plot, my 1, 1, 2, 2, 3, 3, etc. And it should be a nice reflection over this line y equals x. Our third example gets a little more exciting. So we have f of x equals 2 to the x. Now right away, your gut has to tell us exactly what this function should look like. We just spent a good month practicing these functions. This is an exponential function. Okay, why does your gut have to say that right away? Well, you have a base to a power, and that power is a variable. So that's an exponential function in the form y equals ab to the x. So I'm going to start with a graph of this function. What does it look like? Does it even have an inverse? So here's our function, f of x equals 2 to the x. Now there's lots of special things about this exponential function. You'll recall that it crosses through that point 0, 1, so let's go ahead and get that labeled in your notes there. It's also asymptotic. This graph gets closer and closer and closer. Notice it's getting close to this line, so that's where the asymptote is. Now your calculators don't graph that, but you do. You have to graph those asymptotes when you graph exponentials. Okay, a horizontal line like the horizon is y equals 0. So does this function have an inverse? Well, we know it's a function. It passes the vertical line test, and it does have an inverse because it's going to pass the horizontal line test. Now, some things to talk about this exponential as we review here. Notice the function's increasing. When I go from left to right, this function goes up, it gets larger, its slopes are positive. It's increasing. And we call this increasing at an increasing rate. Remember, the slope here is pretty close to 0. It's a flat line almost. But as you get bigger, would you say the slope gets bigger? Gets steeper? Picture it as skiing. If you're really afraid of skiing, you probably want to stay on a hill like this. But the more of a daredevil you become, the steeper you get. So I would say it's increasing at an increasing rate, meaning the slopes are getting bigger. So the inverse is going to do the opposite. It's going to increase, but not at an increasing rate. Hopefully it's increasing at a decreasing rate. So let's go ahead and find that inverse. Now, we could already label a point on this graph for sure. If 0, 1 is on the original function, then 1, 0 better be on the inverse. So I know that 1 point for sure. Okay? But we'll go ahead and find it by hand. So f of x equals 2 to the x. Okay, remember that's really like y equals 2 to the x. We're going to switch those x's and y's. X equals 2 to the y. All right, now the million-dollar question, how do you solve an exponential equation? Well, you take the log of both sides. So I'm going to say the log of x. Remember, we're going to use log properties. This exponent is going to come down in front. So y times the log of 2. And then I'll simply divide the log of 2 over. We've been doing this for quite a while now. And y equals log x over log 2. Now, we're going to go a lot further with that. We talked previously about the change of base formula, so let's go ahead and review that. We said we can take any log in the world, let's say log base b of x, and we can put it to any base we want. Remember, this little guy goes on the bottom. So I can say it's the log of whatever base a of x over log base a of b. And we said all we had to say is this number goes on top, base goes on the bottom, and you put your own base in that you want it to be. So what I want you to do is kind of go backwards. So stay with me here. Do you see how this equation here looks like this piece? I want to go backwards and basically make one log out of this. So let's take that and go backwards. This number just goes here, and this number just becomes my base. So I'm going to apply the same thing here. Okay, I'm going to take this top number and put it there, and the bottom number just becomes my base. So this is really log base 2 of x. So what does that tell us? Well, graphically, it tells us that an exponential and a logarithm are inverses of each other. And that is the key, my friends. An exponential and a logarithm are inverses. So let's get that jotted down, star it. An exponential, I'll say it one more time, and a logarithm are inverses of each other. All right, so we're going to try a similar one. I'm going to move a little quicker. F of x equals 4 to the x minus 3. So again, your gut's got to say exponential. The exponent is in the variable. So let's go ahead and solve. We'll switch that x and y. So recall that is really y equals 4 to the x minus 3. That's the whole exponent. Let's wrap it in parentheses. We'll switch that x and y. X equals 4 to the y minus 3. All right, so remember, to solve an exponential, we use logs. So I'll take the log of one side, and I'll take the log of the other, but it just takes that whole exponent and moves it down in front. Okay, so my goal is to get that y by itself, so I'm going to divide both sides by log of 4. Okay, so right now I have log of x over log of 4, so I'm going to go backwards in my change of base and say that's really the log of, the base was on the bottom, so log base of 4 of x equals y minus 3. And then I'll solve for y, so I get log base 4 of x, put the of around it, and I'm going to add 3 equals y. All right, so again, we're going to verify that those two are inverses by graphing this function in the original. Now, be careful how you type this in. Notice the x is the only thing that should be in that set of parentheses. So here's a nice picture of my graph you'll see. I have my exponential, which is increasing at an increasing rate because it's getting steeper and steeper and steeper. And then you'll see my log is still increasing. I'm going up from left to right, but it's at a decreasing rate. Here, I'm really, really steep, and then I get less and less and less and less and less steep. So I'm increasing at a decreasing rate. Before we dive into the next example, I just wanted to review converting from log to exponential. And we said in class, we tried to keep stressing begin with the base. And remember, the base is the little guy, so just kind of put a circle around it. We want to begin with the base, and we said we'll kind of go around the world. We'll start here, we'll go out and come back in. So in exponential form, this is 2 raised to the y equals x. Begin with the base, go out and come back in. Do you see how the 2 is touching the x? It shouldn't happen over here. Okay, this base has to touch the other term. Just keep saying begin with the base. So log base 4 of x equals m, begin with the base. So 4, it's currently touching the x, don't let it touch again. Go around and back in. 4 to the m equals x. And we'll use that in the next example. All right, so this time we're going to start with a log graph. So f of x, we already know log has an inverse, it's an exponential. So f of x equals 3 log of x squared. So again, that's really y equals 3 log of x squared. And I'm going to switch those x's and y's. X equals 3 log of y squared. Now before I attempt to solve for y, you'll notice a log property is already hidden in there. You have an exponent in this log. And where do the exponents go? Well, that law 3 says the exponent comes down in front. So I'm going to say this is actually x equals, if I bring that 2 down, I get 3 times 2, which is 6 log of y. Okay, now again, my goal is to get the y by itself, so I can divide both sides by 6. So I get x over 6 equals log of y. So now we're going from log form to exponential. We're not going to take the log of both sides. The log is already there. We basically want to get rid of it. So remember, in a common log, when there's no base here, you got to put your own base in of 10. If it was a natural log, I'd use the base of e. And we talked about this, our silly little thing was to kind of go around the world to get it, begin with the base, and go around and come back in. So I'm going to say this is actually begin with the base, 10 to the x over 6 equals y. And again, we just covered that last week. 10 to the x over 6 equals y. So this is going from log form to exponential form. Okay, again, exponential, the variable is the exponent in the form y equals ab to the x. And again, we could graph both, show that the reflections over the line y equals x. Our last example tonight has one tricky little piece in it, so be very careful here. F of x equals x plus 1 over x minus 1. So again, I'm going to rewrite it as y equals x plus 1 over x minus 1. Okay, so I'll switch those x's and y's. X equals y plus 1 over y minus 1. Now, what's the tricky little piece, guys? Well, we've never solved one that has two y's in it. We've always gotten one y by itself. So that's the tricky piece to it. So my gut says, I'm just going to put, I'm going to put this over 1, and I'm going to cross multiply. So 1 times anything is itself, so that's just y plus 1. I'm carefully going to multiply here, so I'm going to say that's x times y minus 1. Okay, so I'm going to take my times, so I'm going to say that's y plus 1 equals x times y minus x. All right, so remember, when you want to solve for y, you have to get the y's on one side and solve. So I'm going to have to rearrange this a little bit. I'm going to leave this y. I'm going to bring this guy over to the other side, so I'm going to subtract xy. And I'm going to bring this 1 over to the other side, so I'm going to say negative x minus 1. All right, so here's the part that people miss. How do you get these y's by themselves? This is not by themselves if there's two y's there. What can I do to get the y by itself? Okay, and if you haven't noticed, half of algebra, probably 75% of algebra, 90% of algebra, comes back to factoring. Okay, you can factor the y out, so it's alone. I'm going to pull out a GCF of y. So when I pull the y out, it doesn't disappear. Remember, you're saying y divided by y is 1. Then there's a minus sign. And xy divided by y is just x. Now I can get that 1y by itself by dividing the quantity 1 minus x over. So I would say y equals negative x minus 1 all over the quantity 1 minus x. Now, let's say it's multiple choice and that wasn't the answer. I just want to be clear on a very equivalent answer. You can change all the signs in the answer's equivalent. So instead of saying negative x minus 1, I could have positive x plus 1. And instead of having positive 1 minus x, I could have negative 1 plus x. So I just want to be clear, as long as you change all the signs, these are equivalent answers. Now, do they cancel to a negative 1? Well, no, and don't fall into that trap. This one is positive and this one is negative, so they are different by a negative, but this x is negative and so is this one, so those do not simplify. This is as far as we can go. So the trick in that one, like I said, was to be very careful and factor. Well, we'll get a lot of practice tomorrow in class, so have a great night.